Welcome to another video. Our previous video talked about how we can use backwards recursion and maximum likelihood together to estimate the parameters of the utility function of our dynamic discrete choice model. Now, as you might recall from the first video in this mini-series, I briefly talked about the time horizon being finite or infinite. And it turns out that there are many applications in economics and other domains where an infinite horizon model is more appropriate. So in this video, I wanted to cover how we can modify the concepts that we covered in the previous video with a finite horizon to the case where we have an infinite horizon. And this will set us up to better appreciate the seminal Rust bus engine replacement model, which we'll cover in the next video after this. So let's jump right in to what the conditional value function looks like if we have an infinite horizon. And because we have an infinite number of time periods, we're just going to denote t plus 1 with an apostrophe or a prime, and the current period is not going to have a prime. This is fairly standard notation in other areas of economics that do dynamic programming problems. And we can specify that this continuation value is composed of both a state transition expectation and an Emax term over the future conditional value functions. So this should be very familiar to you. We've just put a prime on the epsilon and the x in here to denote that that's the future period or the continuing periods values. So if we have a type 1 extreme value error term, then this Emax term has a closed form, and then we can write the conditional value function as you see here. And again, don't forget Euler's constant times beta. And the key insight that I want you to take away is that we have a v on the left-hand side, and we also have a v on the right-hand side. And because we have an equation where the v's are on both sides, we need to do what's called solving for a fixed point to make sure that we get the model solved for, that we get the right policy functions coming out of this model. And the reason that we can do this is because there's a contraction mapping. And I don't want to get into all of the math and the theory there, but you can do that on your own time. So let's see how we can actually operationalize this procedure. So let's denote squiggly x as the number of states that x can take on. We're going to stack these conditional value functions for every possible state and every possible choice. So the first squiggly x rows of our system of equations is going to just be for the conditional value function for choice 1. And then the last set of squiggly x rows of our system are going to be for the value function for choice capital J. And then we have a very similar structure for any choice in between. So there's a lot of equations here, and we have all of our conditional value functions corresponding to whatever the little v is on the left, defined as they were on the previous slide. So once we do that stacking, we can more compactly write this system of equations as v equals u plus beta times t of v. And t is just going to represent the expectation operator, where that expectation is taken over both the epsilons and the state evolution. So how do we actually solve this? Well, we're going to plug in values for the parameters, the alphas or the betas or the gammas, and we're going to guess what the v's might be. And then we're going to substitute in for the v's on the right-hand side, which is going to give us a new set of left-hand side v's. And then we're going to just iterate on this until we get convergence in the v's. So what's the best way to substitute in? Well, that's going to be defined by some algorithm that we choose. In much the same way that we don't really think about, well, how do I update the parameter value for my likelihood function in between iterations? It just comes out of the algorithm that we chose to do. So just to kind of formalize this, we're going to iterate. We're going to set v of n plus 1 is going to be this right-hand side system evaluated at v of n, and then we just update this, and we recursively set the next period's v's as the previous period's v's, and then just iterate until convergence. So I think I misspoke. I don't even think there's an algorithm here. We just have the definition. By definition, there's stuff on the right-hand side that is going to be equal to the stuff on the left-hand side, and we're just going to iterate until those things become equal or less than some small value called delta. So our complete estimation steps for the infinite horizon case are going to look very similar to the finite horizon case. At the outer loop, we guess parameter values for whatever the parameters are, call it theta. And then we're going to solve the inner loop using this iterative fixed point algorithm. Sometimes people call this value function iteration. Then once we have that solution, then we calculate the choice probabilities at all of the solved conditional value functions at all of the states, evaluate the likelihood, and then update the parameters of the likelihood according to whatever nonlinear optimizer we're using, LBFGS, for example. And then we just repeat both the inner loop and the outer loop until we get convergence in the likelihood. So this algorithm was made popular by John Rust's work, and it's also called the nested fixed point algorithm, or NFXP, because it's got this fixed point iteration in the inner loop. So now that we have an appreciation for how an infinite horizon model is solved and estimated, now we can actually talk in an informed way about John Rust's seminal paper from 1987, modeling bus engine replacement decisions. So I hope to see you in that video, and thanks for joining.